Chapter 11, liquids, solids, and intermolecular forces. This is kind of interesting. So, you've probably observed that lizards can climb walls, right? These geckos can climb even a really smooth surface like glass. You're like, how do they do that? You know, Spider-Man isn't real, and you can try doing that. It's not going to work. How do they do that? Well, if we look at their feet are very specialized, and if we look even further, we see that they've got these little, like almost tentacles with these, it almost looks like a toothbrush or something with the little frayed ends. And so they've got all these little tiny ends. And it's actually intermolecular forces between all these little ends and the surface that they're crawling on that allows them to defy gravity and climb up a glass window. It's really pretty amazing. Intermolecular forces. So we're going to learn about what those intermolecular forces are. And that's the last we're going to talk about geckos. So intermolecular forces are forces of attraction between molecules. Hence the name, intermolecular, between molecules. In sports, there's intercollegiate sports. Those are teams, and there's competition between colleges. And then there's intramural sports, and that's where you're competing against other teams at your school. So intra is within and inter is between different things. So intermolecular, between different molecules. So these are not the bonds within a molecule. These are interactions between distinct molecules. These are present in all molecules and atoms, but to varying degrees. These are significant only at very short distances. They are responsible for the very existence of liquids and solids. If there were no intermolecular forces, everything would be in the gas state, and the universe would be a very different place. Intermolecular forces are essential for physiological processes. Your body depends on intermolecular forces. The state of a sample of matter, meaning solid, liquid, or gas, depends on the strength of those intermolecular forces relative to the amount of thermal energy. And we talked about how all particles are in motion. But the particles in a solid object are just vibrating and wiggling, just like you guys in your seats right now. You're fidgeting a little bit, but you're all in the same position relative to each other. But you are moving, and that is thermal energy. So as thermal energy increases, think about someone getting more and more agitated in their chair. Eventually, they're going to be up and running around the room, right? There are forces of attraction that hold the particles together. Those are the intermolecular forces, and those are opposed by the thermal energy. So if it's a solid, that means that the intermolecular forces are fairly strong for the amount of thermal energy at that temperature. So looking at these guys, here's a gas, the three states of water. So steam is what we call water in the gas state. And the particles are very far apart. Remember we said that the strength of those intermolecular forces is significant only at very short distances. When these particles are far apart from each other, they essentially experience no forces of attraction. You think about, I've mentioned the people in Wyoming, the population of Fresno spread out over a whole state. If you spread those people out uniformly throughout the state, they might not even be able to see the nearest person. Would there be much attraction between individual people? It's hard to be attracted to someone you've never met or heard of, right? It just doesn't work real well. So these guys are so isolated and far apart from each other, there's really no interaction. And these have a great deal of thermal energy. Liquid water, the particles are touchingly close. And so they're swimming around, they're moving about, they have more thermal energy than ice. We look at the temperature of water, 20 degrees versus 0 degrees Celsius. Higher temperature means higher thermal energy. Here, the thermal energy and the strength of the intermolecular forces is more balanced, where there's enough attraction that they're staying together, but they're not all fixed into position. In the solid state, the forces of attraction, the intermolecular forces, are winning over the thermal energy. And these particles will be vibrating, but they're not moving relative to each other. They're fixed in position because of these intermolecular forces that are present. Any questions yet? So the big difference between solids and liquids is the freedom of movement of the particles. There's not much difference in density or how close the particles are, but the difference is how free they are to move. So in a liquid, there's enough thermal energy that they can break away from their neighbor and move over, but then they're attracted to the next neighbor, and there's this continuous forming and breaking of attractions. In a solid, the particles are just locked in position. Excuse me. So we've talked about these ideas before, that gases have low density, liquids and solids have high density. Shape and volume are different for these. And these are related to the strength of the intermolecular forces relative to thermal energy. In a gas, the intermolecular forces are weak. In a liquid, they're moderate. And in a solid, they're strong. The thermal energy can change. It changes with temperature. And so that's why you can have one substance and it could be in different states, but that will happen at different temperatures. We've kind of talked about this before too. Gases are compressible because the particles are so widely separated. And you can push down in the plunger and you can squish them together, and there's plenty of empty space for them to squish into. When you take a liquid where the particles are already touching each other and you try to press it together, it doesn't work very well. You can compress it a tiny bit, but there's really no empty space to squeeze out. They just cannot get any closer. I mean, if you start cramming people in an elevator, eventually there's just no more people that you can fit in the elevator because there's no more space. That's how liquids are. We've also talked about different kinds of solids, crystalline and amorphous. The crystalline solid has a regular repeating structure. It's ordered. There's a pattern to it. The amorphous solid has no particular order to its pattern. It's very disorganized and messy. We're familiar with state changes because of temperature. If we think about ice melting to liquid water and then evaporating into the gas state, that goes on around us all the time. So what happens is, as you heat it up, the thermal energy of the particles increases. One way to think of these intermolecular forces as stick-togetherness, or in some ways it resembles Velcro. Okay, so you think of these particles all Velcroed together. You've seen those bounce houses with the Velcro wall, and you put on this suit and you jump and you stick to the wall, right? It's like, I'm not sure why we think that's fun, but people get a big kick out of doing that. Well, so imagine a bunch of people in Velcro suits and they're stuck to each other. How could they get loose? You have to move, you have to jerk and pull away, right? You need a certain amount of motion to pull away. And so as the temperature increases, the motion of the particles increases and they're able to move around. And then when the thermal energy increases even more, they have so much energy that they can just break away from the pack and go off by themselves. When you get away from the Velcro, it's not going to attach to you anymore. It's only while you're really close to it. And the opposite process happens as the gas cools down and loses thermal energy and gets slower and slower. Then when these two particles run into each other, think about two people in Velcro suits running into each other. If you're moving really slow, you're going to stick to the person, right? If you're moving really fast, you might have enough residual momentum to break off again. As the gas slows down, when it collides with itself, with other particles, they're going to stick together and it's going to condense into a solid. As the condense into a liquid. As the liquid particles slow down, they're going to get stuck in position and be a solid. So we're familiar with that. But changes in pressure can also cause transitions between gas and liquid states. I think most of us are familiar with gas grills and propane cylinders. Even if you don't have one, you see them outside convenience stores and Walmart and stuff. So there's this propane tank. It's LP gas. LP is liquefied petroleum gas. Okay, it's mostly propane. Why is it a liquid? It's a liquid because they shoved so much of it in there and it's under such high pressure that it's squeezed together and it becomes a liquid. The advantage of that is you can get a lot more propane in the cylinder than if it was in the gas state. If you wanted enough propane in the gas state to cook a steak, you'd need this ginormous tank of propane. So high pressure, remember we talked about non-ideal gas behavior, and high pressure, you're squeezing the molecules together. That's where it doesn't really obey the ideal gas law anymore. So under high pressure, it will liquefy. When you open this valve, the gas wants to get out, right? It's going to go from a high pressure situation to a low pressure. When you let it out, it's in a low pressure situation and it vaporizes again. And then the gas goes into your grill and you spark it and light it on fire and you cook your steak.